In the previous video, we began Unit 2 by revisiting ionic bonding. Today, we revisit covalent bonding. Covalent bonding, if we remember, is the bonding that occurs between atoms that have similar electronegativities. In most cases, covalent bonds form between two nonmetals, as opposed to ionic bonds, which most often occur between a metal and a nonmetal due to the vastly different electronegativities between elements of those classifications. We should also remember that covalent bonds can either be nonpolar or polar in nature. The polarity of a bond is determined by how big a difference in electronegativity there is between two atoms. Polarity is essentially a measure of how lopsided a bond is. In a polar bond, one atom is significantly more electronegative than the other, and therefore pulls electrons strongly toward itself. Thus far, we've talked about electronegativity as being a purely qualitative parameter. In other words, we've never tried to attach numbers to electronegativity. The reason for this is that it is important to emphasize that electronegativity isn't exactly something that can be measured. Something like electron affinity, on the other hand, can be measured because it's the energy released when an electron is added to an atom. We can measure energy and give it a numerical value, so electron affinity is a quantitative value first and foremost. Electronegativity, however, is not, and I wanted to make sure I didn't confuse anyone. There is, however, a scale for measuring electronegativity. This scale is called the Pauling scale, and it is named for Linus Pauling, the American chemist and chemical engineer who came up with it. An interesting fact about Linus Pauling is that he is the only person in history other than Marie Curie to have received Nobel Prizes in two different fields, one in chemistry and one Nobel Peace Prize. The scale he came up with assigns numerical values to elements' electronegativities on a comparative basis. What we mean by this is that the scale compares the electronegativities of the elements and then puts them on a number line by comparing how strongly they pull electrons toward themselves. One way to think about this is to think of the pain scale that you might see hanging on a wall in a doctor's office. A pain scale is usually a piece of paper with lots of different faces printed on it, each labeled with a number between 1 and 10. A doctor or nurse will use the scale to ask a patient how much pain they are currently in. Pain is obviously unique to each person and can't be measured using numbers, but it is possible to compare one type of pain to another. If the pain from getting a paper cut is a 1 on the scale, then the pain from burning yourself on a hot pan might be a 5 on the scale, and breaking your arm might be an 8 on the scale, and so on. The Pauling scale works the same way. We can quantify electronegativity by comparing the electronegativity of one element to others. Here is a PubChem periodic table with the electronegativity values the Pauling scale assigns to each element. Now, we know that the difference in electronegativity between two atoms determines what type of bond forms between them. With our new knowledge of the Pauling scale, we can set numbers to these differences. If the En, or electronegativity, difference between two elements is less than or equal to 0.4, a nonpolar covalent bond will form. If the En difference between two elements is between 0.5 and 1.7, a polar covalent bond will form. If the En difference between two elements is greater than or equal to 1.8, an ionic bond will form. When representing covalent bonds, the lowercase Greek letter delta is often used to show which atom is more electronegative. The lowercase letter delta, by the way, has always looked like a cherry to me, so I always draw it the way it's shown here, but this is probably not exactly correct. If anyone knows a better way to write this letter, do let me know. In any case, we can place a minus sign next to the lowercase letter delta to show that an atom is more electronegative and that the bond will be lopsided in its favor. For example, here we have a bond between nitrogen and hydrogen. Nitrogen is more electronegative than hydrogen, so we draw the lowercase delta followed by a minus sign on top of the element symbol for nitrogen. We then draw the lowercase delta followed by a plus sign on top of the element symbol for hydrogen to show that hydrogen is less electronegative. We know that ionic bonds involve the so-called transfer of electrons from one atom to another. If more than one electron is transferred, we simply write the ion as having a higher charge. When we try to visually represent covalent bonds, though, we have to use a different schematic. When an atom is sharing more than one electron with another atom, we need to draw the bonds between the electrons to show that they are being shared. This is where we get the concept of bond order. Bond order is simply a measure of how many electrons are being quote-unquote shared between two atoms. Another way of saying this is that it represents the number of covalent bonds that have formed between two atoms. That's all bond order is at the end of the day. Let's look at an example of this. Here we see the covalent bonds that form in a molecule of CO2, or carbon dioxide. As we can see, we have the element symbol for carbon, the two uppercase letter O's which represent the oxygen atoms, and then we have these lines connecting the oxygen atoms to the carbon atom. Each of these lines represents a pair of electrons. I've gone ahead and drawn the electrons being shared in each bond in red to make this easier to understand, but do remember that a real drawing won't show these shared electrons. It will only show the line representing the covalent bond. In this case, each oxygen atom is sharing 2 electrons total with the carbon atom, and the carbon atom in turn is sharing 2 electrons with each oxygen atom. Because of this, there are 2 lines connecting each oxygen atom with the carbon atom. What do we think the bond order is then? The bond order in this case is 2, because these are double bonds. Remember, if there is 1 bond or 2 electrons being connected by a line, we call that a single bond. If there are 2 bonds or 4 electrons being connected by 2 lines, we call that a double bond. If there are 3 bonds or 6 electrons being connected by 3 lines, we call that a triple bond. There is such a thing as a quadruple bond, but these are so rare that we will almost never encounter them in a general chemistry course, so we're going to ignore them for now. Let's get into some example problems to make sure we haven't lost ourselves. Example 1 says, what is the bond order of the chemical bond in diatomic oxygen, or O2? Feel free to try this one yourself. We know that a single oxygen atom has 6 valence electrons. This means that for 2 oxygen atoms, there is a total of 12 valence electrons. But according to the octet rule, each oxygen atom wants 8 valence electrons, or 16 total if we're talking about the pair. Because of this, we need 4 valence electrons to be shared through covalent bonding, because 16 desired valence electrons minus 12 existing valence electrons equals 4. If 4 electrons are being shared, that makes for 2 electron pairs, and each pair needs a single bond. So we need 2 bonds. That means that bond order is 2, and a double bond will form in diatomic oxygen. Example 2 now. What is the bond order of the chemical bond in carbon monoxide, or CO? Carbon has 4 valence electrons. Oxygen has 6. So we have a total of 10 existing valence electrons. Both atoms want to have 8 valence electrons, so a total of 16. If we calculate 16 minus 10, we get 6. 6 valence electrons means 3 electron pairs, and 3 electron pairs each need 1 bond, so a total of 3 bonds. This makes the bond order 3. And a triple bond will form in carbon monoxide. Now that we've talked about both ionic and covalent bonding in detail, we need to introduce another type of diagram. These diagrams are called Lewis structures, and their purpose is to show the valence electrons and the bonds of atoms. These structures use dots to represent valence electrons, lines to represent bonds, and element symbols to represent the atoms themselves. Before I confuse you too much, let's look at an example. This right here is the Lewis structure for a fluorine atom. The atom itself is shown by the element symbol, a capital letter F. Each of these dots drawn around the letter represents a single valence electron, and if we count them all up, we'll see that there are 7 in total. Now, it's important to mention that it does not matter how exactly these dots are positioned. This lonely dot on the bottom could just as easily have been placed on the left-hand side, and it would make no difference. The only rule is that it is generally considered good practice to have a maximum of 2 dots on any given side. This way, if an atom has a total of 8 valence electrons, we can have 2 dots on each of the 4 sides and make it look nice and symmetrical. Make sure to follow that rule. Down here we have the Lewis structure for a molecule, sulfur dioxide or SO2. Sulfur dioxide, by the way, is a very common air pollutant, and it is a common byproduct of a lot of different fuels when these fuels are burned. It's also one of the primary gases that make up the atmosphere of the planet Venus, and sometimes it condenses into sulfuric acid and rains down on the surface there, which is pretty interesting. Anyhow, the Lewis structure for sulfur dioxide shows the element symbol for sulfur and 2 uppercase letter O's to represent the oxygen atoms. Each oxygen atom has a double bond connecting it to the sulfur atom. These dots on the atoms that are not a part of the bonds are called lone pairs. There's no need to know too much about lone pairs at the moment, but they do become important when we start talking about Vesper theory and other more advanced topics in molecular geometry. For now, all we need to remember is that lone pairs are pairs of valence electrons that are not involved in a bond. Lewis structures frequently come up on exams, and a common test question is to ask the student to draw a Lewis structure for an atom or molecule. So here is a quick procedure for drawing Lewis structures. The first step is to add together all the valence electrons of all the atoms involved. This will give us our existing valence electron number. The next step is to choose the most electronegative atom to be the central atom, or the atom that all the others are bonded to. In our sulfur dioxide example, up here for instance, sulfur is more electronegative than oxygen, so it was the central atom. Both oxygen molecules are bonded to the sulfur atom and not to each other. Step 3 is to draw a single bond between the central atom and each of the other atoms, which we'll call surrounding atoms. Step 4 is to add the remaining valence electrons in pairs to the surrounding atoms until octets are achieved. The fifth step is to add whatever valence electrons are left to the central atom. The sixth and final step is to draw double and triple bonds wherever this is possible. The best way to understand a procedure is to test it, so let's do 3 example problems. Example 3 would like us to draw a Lewis structure for methane, or CH4. Step 1. Find the total valence electrons. Carbon has 4, each hydrogen has 1, so that becomes 4 plus the parentheses around 4 times 1, or 8. Step 2 is to choose the central atom. Carbon has a Pauling electronegativity of 2.55, and hydrogen has one of 2.2, so carbon is our star of the show. it goes in the middle as our central atom. We then draw the 4 hydrogen atoms around it, like so, and then draw a single bond from each hydrogen atom to the carbon atom to complete the third step. There we are. In step 4, we know that 8 valence electrons total have been added to the structure because of these single bonds. Each of the hydrogen atoms shared 1 valence electron, and the carbon atom is sharing 4 altogether. We might remember that hydrogen is one of those sneaky exceptions to the octet rule in that it only needs 2 valence electrons to be stable. Oxygen also already has 8 valence electrons, 4 that it had from the beginning, and 4 that it's sharing with the hydrogens. This means that we have no more valence electrons to account for, since 8 minus 8 is 0. We can actually stop here. This is the Lewis structure for methane. Example 4 says, draw a Lewis structure for carbon dioxide, or CO2. Carbon has 4 valence electrons. Each of the oxygens has 6. So we have a total of 16. Carbon is more electronegative than oxygen according to the Pauling scale, so the former is our central atom. We draw the single bonds. Each bond represents 1 electron pair, and we have 2 bonds, so that's 2 electron pairs or 4 valence electrons already taken care of, and 16 minus 4 equals 12. We need to add these 12 electrons to the 2 surrounding atoms, the oxygens, until both have octets. Each oxygen already has 2 valence electrons due to the single bond, so we add 6 to each oxygen to give them 8. Remember, we have to add these in pairs. So if we had 13 valence electrons remaining, we wouldn't add 6 to each and then throw the remaining 1 electron on one of the oxygens. We would instead place the remaining 1 electron on the carbon atom. In this example, though, we've already dealt with all 12 valence electrons, so there's nothing to add to the carbon atom. All we have left is our final step, which is to add double or triple bonds. Because the carbon atom has only 4 valence electrons at the moment, we can make both of these single bonds into double bonds by drawing the bonds like so. This is the Lewis structure for carbon dioxide. For example 5, we're going to do something a bit different. I'm not going to go through and solve this one step by step. Instead, try to go ahead and solve this for yourself, and I'll write down the answer so we can compare. Example 5 would like us to draw a Lewis structure for water. Feel free to pause the video now if you'd like to do it this way, or you can keep watching and see what the final answer is. That is my Lewis structure for water. Your own diagram, if you drew one, should look roughly similar. The arrangement of the atoms might look a bit different, and the way the dots are positioned might vary, but overall, the bonds and the number of valence electron dots should be the same. One last note before we close. We previously looked at atomic diagrams called Bohr diagrams, although we didn't exactly give them that name then. These diagrams look like this one on the right, whereas Lewis structures look like the drawing on the left. Both these structures are commonplace in chemistry, and each have their uses, but they are different. Lewis structures are only concerned with valence electrons and the bonds that form when atoms share valence electrons. Bohr diagrams, by contrast, are concerned with all the electrons in an atom, as well as their distribution in said atom's electron shells / energy levels. Lewis structures are, by and large, more useful when discussing bonding and molecular geometry, while Bohr diagrams find greater application when talking about atomic structure and electron configuration. In our next video, Unit 2, Video 3, we will introduce polyatomic ions. Thank you for watching.